Man's study of dynamics has opened up new frontiers of science. His work in hydrodynamics has brought greater speed and diving ability to the nuclear submarine. His application of aerodynamic principles to rocket-boosted aircraft has produced a piloted airplane that has reached the fringes of space. Now he has a new challenge, to seek out and determine the nature of soil beneath the surface of the Earth. Terradynamics is a term chosen by Sandia Laboratory to describe the scientific study now in progress to determine what physical changes actually take place underground when a projectile penetrates and lodges beneath the Earth's surface. Terradynamics is related to both hydrodynamics and aerodynamics, but instead of dealing with the relationships of a vehicle to either fluid or atmospheric environments, this new science is concerned with the movements and resistance of various Earth materials to the penetrating vehicle. Since the materials near the Earth's surface range from very hard igneous rocks all the way to water, it is apparent that such a study is extremely complex. In fact, the fundamental physical phenomena involved in penetration have not yet been analytically solved. Sandia Laboratory has, however, made significant progress toward a theoretical solution of the problem through controlled laboratory research and full-scale field testing. We have conducted tests into a wide variety of Earth materials and recorded the deceleration forces experienced by the impacting vehicle. The materials investigated include loose to dense moist sands, dense cemented sands and gravels, soft muds, stiff moist to saturated clays, hard, dry, silty clays, dense gypsite, glacial ice, and salt water. We have also penetrated such intact bedrock as dense sandstone, granite, welded tuff, and dacite. Sandia's penetration vehicles vary from 3 to 18 inches in diameter and from 3 to 15 feet in length. Nose shapes range from flat to needle-pointed. Although exterior configurations may differ slightly, the essential elements are fairly standard. The vehicle nose, whether it is sharp or flat, is always solid metal. A hollow afterbody contains the onboard telemetry package and any other equipment needed for the test. The aerodynamic fins stabilize the unit in flight, but are designed to break off on impact. Each aerodynamic fin is set in a small bracket that remains on the vehicle after penetration. We call these brackets terradynamic fins because they seem to help the unit maintain a stable underground trajectory. Another factor controlling subsurface stability of the vehicle is the length to diameter ratio. A ratio of 10 to 1 is considered minimum. A telemetry package within the body of the vehicle sends deceleration data and strain gauge time signals to a transmitter at the end of a long trailing line. As the aircraft releases the vehicle, the trailing transmitter is deployed and activated. The trailing line must be longer than the expected penetration depth so that the transmitter will still be above the ground when the projectile comes to rest. Thus, information on vehicle behavior can be transmitted throughout both the aerodynamic and the terradynamic test phases. Under normal conditions, field testing is indeed valuable. The high-speed data cameras record the aerodynamic event, and the telemetry package transmits the terradynamic. But the one record we really want has so far been unattainable in the field. We want to know what actually happens to the subsurface soil particles when a solid steel penetrator is suddenly thrust into their bed. Since photographic data cannot be obtained underground, the event must be interpreted by analyzing the recovered vehicle, paying particular attention to the eroded paint pattern. We know that the vehicle reaches maximum velocity at the moment of impact. Thus, the impact phenomenon produces a strong deceleration pulse of very short duration. As the vehicle continues to penetrate, the aerodynamic fins shear off. This produces a small pulse. While the projectile travels through the earth, the slicing action of the nose shears and compresses a thin zone of soil around the projectile. The soil particles are apparently pushed away from the nose with considerable lateral velocity. Thus, there is little friction on the vehicle body during the major part of the event. As a rule, the paint on the penetration afterbody is only slightly scratched. The soil particles do, however, rebound after the vehicle has passed, causing the trajectory hole to be somewhat smaller than the vehicle diameter. As the vehicle decelerates, the penetration phenomenon apparently changes. The nose, as it approaches terminal velocity, does not displace the soil as violently as it did earlier, and the soil particles manage to rebound before the projectile has passed. Now the soil grips the vehicle and stops it abruptly. For many penetration events, this terminal deceleration is the highest recorded value. We find the data is most useful when deceleration is presented as a function of depth. This way, the main deceleration gradient can be used to provide an indication of the subsoil composition and the vehicle's reaction to it. To help substantiate our theories as to what takes place underground and out of sight, we moved into the controlled environment of the laboratory. Here in 1963, we set up a detailed program to study penetration as it affects different materials under various conditions. Our early tests were conducted into such homogeneous materials as Ottawa sand, gelatin, and plaster of Paris. These tests were partially successful, but it was difficult to obtain accurate data using materials of this nature. A better target medium was needed. Our first step was to select an earth surface material having no cohesion, such as gravel. Then, to simplify the experiment, we established 2 dimensions rather than the 3 found in nature. By using a uniform target material, we eliminated the varying soil densities and compositions encountered at different layers of the earth, and also avoided variations in particle size. With these conditions, we still felt that we could document a meaningful penetration study. To represent the cohesionless granular target medium, we used several thousand precision-ground steel needle-bearing rollers. The rollers were provided in 3 diameters and randomly stacked throughout the target tank. The length of the rollers and the thickness of the penetrator coincided with the inside width of the tank, thus achieving a true 2-dimensional target array. Using steel rollers instead of the actual material provided an opportunity to see and photograph for the first time the exact movements of the individual particles at any given instant during the penetration event. To help follow the movements of the particles when displaced by the penetration forces, a 2-inch square grid of narrow white lines was painted on the front end surfaces of the stacked rollers before each test. A similar grid was painted on the plexiglass cover plate. When bolted in place, the grid coincided with the roller grid and provided a basis for measuring the particle displacement at the termination of each test. The various penetrators, ranging from 1 to 3 inches in width, were mounted on a linear actuator driven by a 28-volt constant-speed electric motor. They were so guided that a reproducible, constant velocity vertical stroke was always obtained. The load measuring and recording system consisted of a load cell connected to a constant speed recorder. Both were calibrated before and after each test series. An electric clock reading in hundredths of a second was placed within the camera view to relate resistance and displacement to time. Sequential photographs were made of each test at speeds up to 4 frames per second using a 35mm camera equipped with a battery-driven motor. This test was one of a series involving several hundred continuous vertical penetrations at various constant velocities. The 3-inch flat-nosed probe will penetrate the roller-bearing target at a constant velocity of 50.8 millimeters per second. The test lasts just 5 seconds, too fast for us to see or analyze the action as it happens. But the photographs taken by the high-speed still camera have recorded each minute detail. By studying these, we can trace the movement of the individual particles. As the penetrator entered the target material, particles greater than approximately 1 projectile width away from the projectile center line began to move toward the surface and away from the projectile. A region called the edge effect zone started to form next to the penetrator. Particles in this area were dragged down with the penetration movement. With the exception of the material directly under the penetrator, this edge effect zone appears to contain the only particles of the target material that were given a downward movement. The width of this zone seems to bear a direct relationship to the width of the penetrator. The wedge zone, that area directly under the penetrator, consisted of a constantly moving mass of material throughout the test. The row of white bearings strung out along the side of the penetrator were originally located in a grid line directly under the center line of the penetrator. As the penetrator proceeded down, the particles passed through this wedge zone and were deposited along the way. The penetration was accompanied by a constantly moving shear front. Although this front resembles the familiar shock wave generated by impact loading, it is not a wave. It is a distinct locus of points at which simple shear is occurring at a given time. We called the target material between the shear front and the penetrator the severe shear zone. All the particles in this area were in a state of continuous shear throughout the penetration event. We believe that the effects of inertial forces on the penetration event become significant in this region. The movements of individual particles within the severe shear zone indicate their displacement upward and outward away from the penetrator. There is, however, a general decrease in density, characteristic of the shearing action in a dense, granular medium. This data, although not giving us quantitative answers, has at least provided a much-needed window through which we can watch the penetration process into one specific type of soil. Through experiments like these, we are beginning to understand the phenomena of particle displacement and shear front formations. But any laboratory test is still an artificial situation. The real penetration problems occur in the field. One recent problem was to develop an equation with which we could predict the total depth of penetration of any vehicle into any soil. We approached the problem empirically. By analyzing the results of over 200 full-scale penetrations into a variety of earth materials, we have developed an equation for predicting penetration depths not only into homogeneous soils, but into layered soils as well. And from the equation has come this nomogram, shown here in simplified form. Each element in the equation is represented in one of the quadrants. When planning a test, we prefer to use the nomogram to determine the predicted penetration depth because it gives us the same results as the equation, but with less effort. Now let's run through a complete test so that we can compare the actual penetration depth with the pre-test prediction. This is a test unit, a 9-inch diameter vehicle weighing 1,050 pounds. The first inputs on the nomogram are the physical description of the vehicle, 9 inches in diameter and weighing 1,050 pounds. The impact velocity is to be 575 feet per second into a dry lake bed target, which, because of prior testing, has been assigned a soil constant value of 5. The flat nose has a coefficient of 0.56. By joining these points, we estimate the penetration depth will be 16 feet. The test is to be conducted into a dry lake bed at Sandia's Tonopah Test Range in western Nevada. The delivery aircraft, an Air Force helicopter, receives the unit and lifts it to the desired drop altitude, 5,000 feet. Impact. Now the critical portion of the test begins, recovery. The crater produced in this type of soil is typically small. As the vehicle penetrates, the displaced soil shears and is heaved up from below for a radius of about 6 feet. This subsurface soil failure causes tension cracks in the Earth's surface, which we mark and record. We saw this same phenomenon earlier in the laboratory with the cohesionless material. After the penetration vehicle is located, the excavation line is laid out and the digging begins. A large bucket drill is first used to sink several shafts in a line to a depth below that of actual penetration. A clamshell is then used to break through the shaft walls and make the excavation one long trench. This type of excavation allows us to make a detailed cross-sectional examination of the upheaval area. Final excavation in and around the penetration vehicle is done with small hand tools, since such important data as soil density changes and shear plane locations are often very subtle and hard to see. Removing the penetration vehicle exposes one major source of data, the soil point. We saw evidence of this phenomenon in the laboratory too, but that material, being cohesionless, resisted compaction. Here in this cemented dry lake playa, 16 feet below the surface, the soil point is packed and well formed. Intact, it is removed to a laboratory where it is cut into 1-inch thick sections for analysis. Our primary method of analysis is X-radiography. By careful control of sample thickness, X-ray exposure, and film development, we can use the radiographs for direct observation and comparison of very slight density variations. For more critical analysis, we use an isodensitometer. This device can scan the radiographic image and read and plot continuous variations of the soil sample density. The answers we get from this type of analysis are very useful in determining changes in soil density resulting from penetration. Now, what of the future? Our studies will continue, of course, but with more emphasis placed on understanding specific soil properties and how each soil reacts to the penetration process. To do this, we are developing fully instrumented projectile systems designed for specific penetration purposes. If we know the decelerations and penetration depth for a given projectile, plus the impact velocity, we can determine the properties of the soil being penetrated without actually being there. This makes feasible preliminary soil exploration from the air. Instrumented penetration probes dropped from an airplane into remote areas or into the sea can send back penetration profile data indicating layers of weak and strong soils, granular and cohesive soils, and bedrock. When fully operational, such a system will have tremendous potential, saving both time and money to users such as the Army Corps of Engineers and the Coast Guard. Since our testing program began in 1960, Sandia has made major contributions to the science of terradynamics. In just 7 years, we have developed projectiles that can survive penetration into all soils and some rock. We have developed instruments that give us data during subsurface penetration. We have discovered a means of empirically predicting penetration depth with reasonable accuracy. But most important, we are gaining an understanding of the various phenomena of Earth penetration.